Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to be talking about heats of formation. Now, wherever you see this term, heat of, really that just means enthalpy change. So heat of and enthalpy change, they mean the same thing in chemistry. And this little f here means formation. Now, what that essentially means is that we need to write a chemical reaction that talks about the formation of a compound. And there's three general rules that you need to follow. Rule number one is that you got to make only 1 mole of a product. And that's going to be kind of interesting with some of the problems that we're going to do here in this video. Okay. Number two, the elements have to be reactants. And number three, that those elements have to be in what we call standard state. This circle right here is what means standard state. And that means we're at room temperature, or 25 degrees Celsius, which is equivalent to 298 Kelvin, and 1 atm of pressure. So a problem could be something like this. It would be like, write an equation for the heat of formation and then fill in the blank of the compound that you want to talk about. Maybe this first compound that we're going to talk about is propane, which is C3H8. So once again, the prompt is write an equation for the heat of formation of propane gas. Now, propane gas has a formula of C3H8. And what we need to do is we need to write an equation for the formation of this compound. Okay, so this compound is going to be a product, so it's going to be on the right-hand side of the arrow. Okay, the reactants are going to be the elements that this compound consists of, which is going to be carbon, which is a solid at room temperature, and hydrogen gas. Now, hydrogen is diatomic, and it's a gas at room temperature. Okay, remember, the elements are going to be in standard state, which is room temperature, or 25 degrees Celsius. Now, if we're going to balance this out, there's 3 carbons on this side. So there has to be 3 carbons on this side. There's 8 hydrogens on this side. So there's going to be 8 hydrogens on the left-hand side. So I'd have to balance this with a 3 and a 4, okay, in order to get the same elements on both sides of the reaction. Now, the enthalpy of formation for this is, I'm going to look this up in a textbook. It's typically in the appendix, or kind of like a whole bunch of tables of thermodynamic values. Okay, you could find it there as well. And the heat of formation is going to be equal to, for propane, negative 103.85 kilojoules. Now, these heats of formation are typically negative, and that's because elements have 0, okay, enthalpy. So our baseline is going to be 0 for the elements, and then when these compounds are formed, okay, remember, when bonds are formed, energy is released, so it's going to be a lower enthalpy. So if our elements of carbon and hydrogen kind of are up here, our 3C and our 4H2, okay, are at a 0 level, then the enthalpy of the propane is going to go down negative 103.85 kilojoules for every mole of propane that we have. So remember, when bonds are formed, energy is released. So from the elements to the compound, it is typically going to be a negative number. Okay, let's try this one more time, but with a different compound that's being formed. What if I wanted to calculate and write the equation for the heat of formation of water, okay, in the gas phase? Okay, so water is going to be my product in the gas phase, and the elements, okay, are going to be the reactants. Okay, well, the elements of water are going to be hydrogen and oxygen. Hydrogen is diatomic and a gas at room temperature. Oxygen is diatomic and a gas at room temperature. Okay, now we need to balance this out. I got 2 hydrogens on the left, 2 hydrogens on the right, 2 hydrogens on the left. And I look over here, I got 1 oxygen on the right, but I got 2 on the left. Okay, And that's where I say this can get a little tricky, okay? Now, normally, if we were doing a regular balanced chemical equation, we'd say, oh, we got 2 oxygens over here. So to get 2 oxygens over here, we would put a coefficient of 2 here, okay? If we did that, we would break rule number 1, which is we're only going to make 1 mole of a product. So there has to be another way that we can balance the oxygens out, and that is we're going to use fractions, okay, as our coefficients. So if I took 1/2 of an O2, okay, that would be equal to 1 oxygen. So half of 2 is 1. Now, on a microscopic level, this would never work because you can't have half of an oxygen molecule. However, on a macroscopic level, like big numbers, you can have a half mole of oxygen molecules. Remember, a mole is equal to 6.022 times 10 to the 23rd molecules of O2. Well, you can simply take half of that, which would be 3.01 times 10 to the 23rd molecule. So this is really talking on a macroscopic level. This is one of the only times that we had ever used fractions, okay, as coefficients. There's a couple other rare instances, but for heats of formation, it's allowed, and that's because you're always making 1 mole of product. So when I look up that enthalpy value for the heat of formation for water, that number comes out to negative 241.82 kilojoules. And remember, that's kilojoules per mole of product that's being formed, okay? So this value is always kind of like it's kind of like implied to be on a per mole value because you're always making 1 mole of the product in a heat of formation equation. So heat of formation equations, 1 mole of product from its elements, and those elements have to be in their standard state. So gas for hydrogen, oxygen for those elements, okay? In the previous problem where we had carbon, the standard state for carbon is a solid. A lot of periodic tables are color-coded to give you the state of matter in their standard state. So that can be helpful, okay? So that's how you write chemical reactions, okay, for the heat of formation of a particular substance.